Welcome, Math 107 students, to Lesson 21 and the demo of Lesson 21 on polynomial functions and their graphs. So we have studied in this class so far two types of polynomial equations: linear equations, which we call degree 1, because the highest power you see in any linear equation is the first power. And in lesson 20, we looked at quadratic functions, and we know that a quadratic function, the highest power that we see is a 2. So today we're going to expand this group of functions so that we can start talking about functions that have degrees higher than 1 and 2. So this whole classification of functions is called polynomial functions. And this is the definition. So I want you to take a few minutes and look over this definition, and then I will come back and see what you understand and what you don't understand. And for some students, this is a really scary thing to look at because it's all letters and they say, wait a minute, what's going on? But look for some patterns, read the instructions, and then we'll take a look at example number 2. Okay, so hopefully you've had a few minutes to try to digest this definition. And just note that it's really hard sometimes to try to represent all possible functions, all possible polynomial functions. So in this case, you've established a pattern here. You say, well, I could be looking at polynomial functions, but one of these terms in my polynomial function will contain the highest power I see. So I'm going to call that a sub n x to the n. That's going to be the highest power that I see. Okay, we call that term, or that helps us to determine what we call the degree of our polynomial function. So this polynomial function has degree n. That's the highest power I see. The coefficient that's multiplying x to the n has the same subscript n as the exponent. So that's how you know that this coefficient goes with this variable expression x to the n. Now, how many other terms follow that particular leading term depends on the polynomial function you're looking at. It might just stop right here. For example, the quadratic function, your parent function, f of x equals x squared, just has this leading term here, 1 times x to the second power. That's it. There's nothing else. Now we know we can have all kinds of variations of this. We could say g of x is x squared plus 2x minus 4. So now we have this first term, the x to the second term. We have the next term where the power here is 2 take away 1. That's our linear term. And here's our a sub naught, our constant term. Okay, constant term here is -4. So notice the pattern that we write this is that you can keep decreasing by 1 all the way down till you get x to the 0 power. Now you might say, wait a minute, Linda, I don't see an x to the 0 power there. But remember, x to the 0 power is just the number 1. So if you multiplied a sub naught times x to the 0 power, it's just like saying a sub naught. So it just represents a constant. One of the key ideas about polynomial functions and why you'll love working with polynomial functions is that all of these exponents are non-negative. That means they're 0. They're either a 0, like f of x equals 4, right, which is just a horizontal line through y equals 4, or they're a positive integer, 1, 2, 3, 4, 5, 6. So you'll never see a negative exponent and you'll never see a fractional exponent. So polynomial functions are really quite friendly. So let's take a look at this first function here. F of x equals 11x to the third minus 6x squared plus x plus 3. So let me give you some terminology. First of all, polynomial functions are a finite sum. In this case, it's 4 terms, a finite sum of terms, 4 terms here. Each term has a coefficient, so this would be your leading coefficient because it goes with your degree, your highest power. So it's kind of the leader of the pack here. Highest power is 3, so we say this is degree 3. And we say 11 is the leading coefficient. And the entire thing, 11x cubed, is the leading term. This next term, minus 6x squared, or negative 6x squared, if you wanted to give it a name, would be the quadratic term. So notice we're going down by a power of 1 here from one term to the next. The next term would have a power of, did I say a power of 1 here? I meant power 2. Power of 1 would be a linear term, and then finally we get our constant term, 3. So our constant term is 3. Now, the really nice part of polynomial functions is you never have to think about the domain, because there's absolutely no real number that's barred from being an input value here. So the domain here is all real numbers, all the set of all real numbers, negative infinity to infinity, parentheses, in interval notation. So that's just some language for polynomials. So we'd say this is a third degree polynomial function. Another way we could describe a third degree polynomial function is a cubic function. That's what we call something that has a highest exponent of 3. All right. What do polynomial functions look like when you graph them? Polynomial functions of degree 2 or higher have graphs that are smooth curves, and they're continuous curves, which means you'd never, if you started graphing one of these, you'd never lift your pencil off your piece of paper. They do not have any breaks or gaps or jumps and no sharp corners. So let's circle the graphs below that represent graphs of polynomial functions. So this first graph, I could put down my pencil here and I could trace this nice smooth curve and without lifting my pen. So this is definitely a polynomial function. This next function, as I start to graph it, notice I have to turn a very sharp corner, boom. So this is not a polynomial function. And you can clearly see in this function that there's a big gap here in your y value. So if I started to graph this one, I would be graphing this. I'd stop here and then I'd have to lift my pen or pencil up and then come back down to finish graphing it. So this is not a polynomial function. And finally, we have this last curve, which we start to trace, and we're curving around, up and then back down, never lifting our pencil or marker off the paper, so that's polynomial. So these polynomial functions, notice your x values, it's the entire x-axis, all real numbers, nice, smooth, curvy graphs. So let's take a look at this polynomial function and talk about some familiar ideas and maybe some new ideas and concepts that we're going to need when we discuss polynomial functions. Now, the first thing I want you to notice about this particular polynomial function is that it's not an addition and subtraction problem, is it? It's all multiplication. So when it's in this form, when it's completely factored like this, it allows us to quickly find our x-intercepts, right, or the zeros of our function. So having it in this form versus the polynomial form where we have plus addition and subtraction all the way across gives us some really key features of the graph. So let's talk about some of these. The x-intercepts, we know that we have this idea of relative maximum and mins, which we call relative extrema, or we can call them turning points. Okay, when the function goes from increasing to decreasing or decreasing to increasing. And we're going to talk about some new ideas today. And when we get to the class activities, you'll have a chance to work with these. And these new ideas talk about the behavior of the graph in two different places. One is near the zero. And remember, the zero is what we call our x-intercept. What's happening just to the left of this zero and to the right of this zero? Notice our function goes from being a positive y value and then at -3 at 0, and then it changes sign to be negative. So it changes sign at this 0. It also changes sign at this 0 right here, but it kind of curves its way through -1. It goes from being a negative value to a positive. But at this 0, notice we didn't change our sign at all. Our sign of our function is positive. We come down here to 0, and then we bounce right back up. You know, we kind of weren't defeated by anything. We bounced right back up into the positive direction. So there's going to be discussion about this idea of the behavior of the graph near the 0. So in your mind, you have to remember that the 0 of a function is what we traditionally were referring to as x-intercepts. Okay, so that's behavior near the zeros. Now, the other major idea we're going to discuss today is the end behavior of our graphs. End behavior. So that means as we move far, far, far to the right, out towards positive infinity, and far, far, far to the left, out towards, did I say negative infinity here? Let's start this over again. As I move far, far, far to the right to positive infinity, and as I move far, far to the left to negative infinity, what is the value of my function approaching? So in this case, I would say my function is increasing. It will always be increasing. It goes towards positive infinity as x goes towards positive infinity. And here, as x moves far, far, far to the left towards negative infinity, my function is also increasing. So notice both of these ends, I refer to it as the arms of my polynomial function, are up in the air like touchdown, right? So these are really new ideas for you today. So we're going to take our time and talk about these today. So to help us with this idea, we have something called the leading coefficient test. So we know that x increases or decreases without bound. That means x moves to the right or to the left along the x-axis towards positive infinity or negative infinity. The graph of my polynomial function can only do two things. It's either going to rise or it's going to fall. Every polynomial function in the end will either rise or fall. It will never do anything but those two things. So what I try to remind students of is to just think about two functions, two variations of two very basic functions. Let's say we have f of x equals x to the first power, and then we'll do the variation on that theme, g of x equals negative x to the first power. Then we'll look at the parent function x squared, and then we'll look at the variation -1 times x squared. Okay, we'll put a -1 there. Well, I've divided this discussion up under the following condition. This exponent is odd, and this exponent is even. So this is an odd exponent, or we would say with our new language, odd degree polynomial. This one is an even exponent or an even degree polynomial. So if you know what these four pictures look like, that will help you to think about any odd degree polynomial or any even degree polynomial. So it's not like you have to memorize all this stuff. You just think about these functions that you are already familiar with. So let's take a look at f of x equals x. What do we know? We call that the identity function. It's a straight line that goes directly through the origin and has a slope 1. What about g of x? G of x is -1 times x squared. And what does that look like? That is a straight line that goes through the origin, but it has a slope of -1. Right, what about x squared and -1 times x squared? Okay, so g of x, h of x here is x squared, and we all know and love this function. We could graph this in our sleep if we were asked to, right? There we go, basic parabola. And the only difference now with j of x being -1 x squared is that it opens downward. Okay. If we took a look at these for 2 minutes and I asked you to tell me if you notice any similarities or differences. So I'm just going to pause this for a minute again. What is similar? What's different? Okay, let's take a look. Okay, I'm back. So I'm going to refer to both the technical terms for this, end behavior, and as x approaches positive infinity, but I'm also going to use a more familiar term and talk about the arms of each of these graphs. And so in the first two situations here, do you see that the right arm and the left arm are going in opposite directions? Right? One arm in this first one, f of x equals x, I would say as x gets really, really big towards positive infinity, my right arm is up. And as x moves towards negative infinity, my left arm is down. They are going in opposite directions. The function here is increasing towards positive infinity, and here your function values are decreasing towards negative infinity. And the same is true with this picture. Here, your left arm is going towards positive infinity, and your right arm is acting opposite of that. Okay. However, with your x squared pictures, both arms are moving in the same direction. In this first case, as x increases and decreases towards positive and negative infinity, both arms are up in the air, moving towards positive infinity. When this second case, when we have -1 times x squared, both arms are heading in the same direction, in this case, towards negative infinity. This will always be true for odd degree functions and even degree functions. Your even degree functions, the arms are always moving in the same direction, whether that's towards positive infinity or negative infinity. Your odd functions, your arms, your end behaviors are going in different directions. Now, what's the key here? The key here is the leading coefficient. The leading coefficient here is 1. The leading coefficient here is -1. When your leading coefficient is positive, this is all you have to think about. Your right arm is always positive. Moving towards, your right arm, I should say, is always up. It's moving towards positive infinity as x gets very large. Same is true here with x squared. Notice, my right arm is up. As x moves towards positive infinity, gets really, really huge, or huge number on the x-axis, guess what? My output value, my y value is always really big. So the leading coefficient, if the leading coefficient is positive, your arm is moving upward. If your leading coefficient is negative, your right arm is moving downward in both of these cases. So you might say, well, what about the left arm? You're only talking about the right arm. Well, Because we just talked about the left arm. If it's odd, the left arm moves in the opposite direction to your right arm. And if it's even, it moves in exactly the same direction. So this is a lot to take in, but just think about these two versions of the basic linear function and quadratic whenever you get confused. Okay, so let's come back here. This is called the leading coefficient test. So this is just a summary of everything I just said. When your degree is odd, your function and your leading coefficient right here is positive. It's going to rise to the right and fall to the left. Okay, so your right arm is up, your left arm is down. When your leading coefficient's negative, it's going to rise to the left and fall to the right. Remember, when it's negative, your right arm is falling. When it's positive, your right arm is rising. And notice your arms are always moving in opposite directions because you have an odd degree. So just think of a straight line. An even degree, think of a parabola, even though this is a lot, fancier than a parabola. We know if we have x squared, we rise to the right and we rise to the left. So when your leading coefficient is positive, you rise to the right, you rise to the left. When your leading coefficient is negative and you have an even degree, you fall to the left, you fall to the right. So that's end behavior, and that's how you use your leading coefficient and whether your degree is even or odd to help you determine the end behavior of your polynomial. So this says the sign of a sub n, that's your leading coefficient, determines the behavior on the far right-hand side of the graph. Is my right arm up, rising, or falling? If n is odd, then the direction of the graph on the left-hand side is opposite the right-hand side. And if n is even, the direction on the left-hand side is exactly the same as the right-hand side. So let's revisit this polynomial we had on, I think it was number 2 or 3 in the demo, where we had this polynomial in its factored form, and talk about the graphical behavior of the graph at the x-intercepts by examining what we call multiplicities. Okay, that's a big word, multiplicities. But somewhere in the language here, maybe you think about multiplication or factors. Notice we have a bunch of factors here. I've condensed it, but if I wrote this out the long way, it would be x plus 3. Let me get the skinny. X plus 3 times x minus 2 times x minus 2, because I've got two factors of that, times x plus 1 times x plus 1 times x plus 1. So we have 3 factors of x plus 1, we have 2 factors of x minus 2, and 1 factor of x plus 3. Multiplying, multiplicities. Okay. So we know that the zeros of this function are -3, because if I plug a -3 into this factor, that makes a 0. So we know we have an x-intercept at -3, 0. So that's one x-intercept. And remember, a 0 is written as x equals a number. It's a solution to this equation. When does f of x equal 0? So when you're referring to zeros, you don't write coordinates. You just write the value of x that makes your function equal to 0, which is -3. We also know that 2, if I plug a 2 in here, I'd get a 0. So 2 is a 0 of this function, and the coordinates 2, 0 is an x-intercept. And finally, x equals -1 would also make this function 0, and that also translates to -1, 0 being an x-intercept. So we now want to talk about the behavior of the graphs at or near, not at these zeros, but just around these zeros, like near these zeros. So let's start our examination of the graph's behavior at the x-intercept -3, 0, or the 0, x equals -3. If we look at the graph near this x-intercept, we would say that the graph passes directly through the x-axis at x equals -3. Notice our graph goes from being positive to negative, passes directly through. And if I use my magic pen here and I just put a little circle around that area and we just focused, oops, my magic pen, well, there it is, okay. So if we look at this area right here, and I asked you what kind of function would look like that, I hope you would say a straight line, a linear function, right? You could make that, it goes directly through at -3. The factor x plus 3 is linear because it has a 1 as its exponent. So it passes directly through just like a line would. And -3 only appears once here because it only has one factor. So since there's only a single factor of x plus 3, we say there is a single 0 of x equals -3, and we say it has a multiplicity of 1. So the multiplicity matches the exponent on your factor. Remember, it has to be in factored form. So let's take a look at filling out the rest of this table here by looking at our other x-intercepts and zeros. So our next x-intercept is -1, 0. Okay. The 0 of the function is the x value, -1. We know if I threw in another little table here, I would say, what does the factor look like? So the factor here would look like x plus 3. The factor here would look like x plus 1. So what's the behavior near the x-intercept? Does it pass through? This one passes through. Does this one pass through? Well, let's take a look. Let's blow it up with our magic pen. Just focus on that. Yep, it goes from being negative to positive. It flattens out a little bit. It doesn't go directly through like it did at -3. It kind of gets really, really close. Then it hits 0, and then it gets a very small positive number, and then it starts to increase, right? Flattens out a little bit, but it's not exactly horizontal in here. If we made this, we kept blowing this up, we would see that there's always space here between the graph and the x-axis. Then at -1 we're 0. So again, we pass through, we change our sign, right? So it passes through, passes through, passes through. And the multiplicity of this 0 was 1. The multiplicity of this one was 3. So they were both odd. Okay, and if you think about this behavior, this looks like an x cubed function. Okay, then our other x-intercept here, let's go back to my regular pen, is 2, 0. And that means the factor looks like x minus 2, because when I put a 2 in here, I get a 0. The 0 of the function is 2. And what does its behavior look like near that 0? So let's come back to this magic pen. We're going to zoom in right on that area, right near that 0. And we see that we were positive, 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 positive. To the left of 2, we became 0. And then we bounced right back up. Doesn't this look just like a little baby quadratic? And that's because the exponent on this 0 is the second power. So this one bounces, doesn't change sign, and it has an even multiplicity. So these two are odd multiplicities, and this is an even. So we know that when you have an odd multiplicity, okay, an odd multiplicity, you are going to pass through your origin. Now, sometimes you go directly through like a straight line. Other times you start to flatten out a little bit. Then you end up coming through the other side. okay, like a cubic or like a straight line. So let me show you this idea of multiplicity and behavior near a zero. So if we look at f of x equals x, it's just a straight line. Here our zero is the number 0. We have an odd function to the first power. Boom, directly through, right? Goes from being a negative value to the left of 0. Our function is negative, and then I take one teeny step to the right of 0, and I'm positive. What happens when I have x cubed? Notice that I still change sign from the left to the left of 0 here. I'm a negative value. In fact, I could keep making this, stretching this out so you can see. I'm negative, and I'm 0 at 0, and then I'm positive. So again, I change sign. But notice I don't go straight through. I flatten out a little, and then I go through. The only thing that happens as this exponent gets bigger is how much you flatten out before you get to that 0. You see, here's x to the 5th. Okay. But the key is that all three of these change sign on either side of 0. The value of your function goes from negative to positive. Okay. It just depends on sort of how flat you get before you get to 0. And you can imagine that the higher I increase this exponent, the flatter that gets. But it's never horizontal, totally. All right, what happens if I play this game? If I now take these three functions off and I change this to be x squared. Well, we know what x squared looks like for sure. And then let's suppose I change my next function to x to the 4th instead of x to the 3rd, x squared. There's x to the 4th. Oops, I got a dollar sign in there. X to the 4th. Okay, we can just look at those two. So there's, oops, still giving me x to the 3rd. I'm going to rewrite the whole thing. X to the 4th. There we go. So see how much flatter x to the 4th is around the 0, but it still bounces. It's still bouncing there. I mean, I could keep making this scale smaller and smaller increments, okay? But it's kind of nice to see the flat bottom comparing that to x squared, okay? Now you can imagine what this would look like if I put x to the 6th in. Can you imagine? Well, let's try it. Let's call it j of x here is x to the 6th. So you make a guess. J of x equals x to the 6th. There we go. Look at how flat that is, okay? So the nice thing about even degree functions, as I mentioned, is that your end behaviors always move in the same direction, either both up or both down. If the leading coefficient's negative, these are just going to reflect over the x-axis. Okay, so that was just a little playing around with GeoGebra. Okay, so let's do the same type of analysis for the x-intercept 2, 0, negative 1, 0, and fill in the next two rows. We've done that. All right. So how do we determine the degree when it's written in this form? Well, if you squared x minus 2, the quantity x minus 2, you would get x squared minus 4x plus 4. And if you took that and multiplied it by x plus 3, you'd get an x cubed. And then if you cube this one out, you'd get at least an x cubed out of it. And an x cubed times an x cubed is an x to the 6th. So I could do that if I wanted to take the time, right? I could do all of that out. And let's see if I remember how to cube this. X cubed plus 3x squared plus 3x plus 1. Okay, and so I could kind of, use my distributive property here, and, it would take forever. But the key idea here is the highest power I'd get from multiplying these first two factors is a cubic with a bunch of terms. And then I'd multiply that cubic times this cubic, and I would get x to the 6th. Well, we're not going to ask you to do all that work. Instead, we just want you to notice that the exponents are going to help us out here. When you have a polynomial that's in factored form only, to find the degree, you just add the exponents. Okay, add the exponents. Because when it's not in factored form, you just look for your highest exponent, right? So here we have a 1 plus a 2 plus a 3. That gives us 6. So this is degree 6. All right, that's a lot of information to take in. So if you want to take a pause between that and go have a snack or take a walk or do something else before you come to this part of the lesson, it might be good to just digest all of that information because it's a lot of new information. So I'm going to assume you've come back and we're going to explore all of these new concepts that we've looked at for polynomial functions and learn how to get a quick sketch, because that's what this is all about. How do we get quick sketches of all these different functions? Now we've seen how to do that with transformations. How do we do it with these polynomial functions? So here is a higher degree polynomial than you've probably ever graphed before without, plugging in various forms of x and then getting the y coordinate. So let's see how we would approach something like this. The first thing I always do is let's talk about the end behavior. We don't wait for the end behavior to be at the end. We want to tackle it right at the beginning. The leading coefficient here is x to the 5th. That's the leading coefficient. And the leading coefficient is 1. So that means my right arm is going to be up. I know my right arm is up. That's all I know right now because my leading coefficient is positive. Okay. That's where I begin. The degree is odd. If I went walking around with one arm up and one arm down, I might look kind of odd, right? With odd degree polynomials, if your right arm is rising, your left arm is working in the opposite direction. It's falling. So my right arm is rising, my left arm is falling. That's the behavior of an odd degree polynomial when your leading coefficient is positive. So now I know my right arm is rising and my left arm is falling. That's interesting. Now I have to solve a polynomial equation. And if you remember way back at the beginning of the course, maybe lesson 7 or 8, we learned how to solve polynomial equations. And that was for exactly these moments. So we want to know, where does this graph cross our x-axis? And then we want to say, when I know where it crosses the x-axis, then I can look at the behavior near those zeros. So we find the zeros by setting our function equal to 0, and we factor this first. The greatest common factor is our friend here. We keep factoring. And now I use exponents to simplify or condense this. And there we go. So we factored it, we've compacted this, and now we set each factor equal to 0 and find our zeros. So x cubed equals 0 when x is 0. So that's one of our zeros. And x minus 3 equals 0 when x is 3. Okay, so I now know my two zeros. Again, I want to reiterate that when you find the zeros of a function, you are solving an equation. You're solving this equation, so your answers are always x equals a number. It's not coordinates for the intercepts. We're not graphing it. We're solving an equation. So 1, 0 is x equals 0. I want to know, does it have an even or an odd multiplicity? My multiplicity here is 3. It's odd. So that tells me that I'm going to cross the x-axis at 3. At 0. The multiplicity is 3. I'm going to cross through at 0. Now, my second 0 is x equals 3. That's an even multiplicity. It has a multiplicity of 2. And that's going to bounce off the x-axis. Now, depending on how flat it is at each of these zeros depends on how high the degree is, the multiplicity is. Okay, like remember, when the multiplicity is 1, it goes straight through like a line. When it's 3, it flattens out and curves a little bit. Okay, so when we find the behavior near these zeros, so let's put them in for 0, 0, and 3, 0. Okay, I know that at 0, 0, I have to cross. I have to go from negative to positive. And at 3, 0, I'm bouncing. I'll never go back down below the x-axis. So here I go. I'm coming up towards 0, and I'm going to flatten out just a little bit. Again, I'm not looking for perfection here. Okay, I'm just drawing my line, and as I come towards 0, then I'm going to continue to flatten out a little bit. And now you say, well, what do I do now? How high up do I go? You know you have to come back down towards this 0, but you'll never go below the x-axis because this 0 has a multiplicity of 2, so you're going to bounce there. And this is just where, you know, you do whatever you want. We don't really care how high up you go. You could go like this. You know, the key idea here is that you cross at this 0, you flatten out a little bit, you come up, you know you've got to come up and come back down to bounce off of 3, 0, and then you're going to rise, rise, rise forever. So any variation of that would be fine in terms of the graph. Okay, so the y-intercept here, when I put 0 in, is also 0. So I didn't have to worry about crossing anywhere else other than at the x-intercept 0, 0 was also the y-intercept. Even and odd symmetry would help you a little bit here, but anytime you have this interplay of even exponents and odd, you're not going to have either type of symmetry. You're not going to be reflecting over the y-axis, and you're not going to be symmetric over the origin. So like I say, this looks pretty odd, right? I mean, well, no pun intended. And again, we're not looking for super duper graphs here, like really, you know, I want to, let's graph this function if I can remember what it was. We had x to the 6th or x to the 5th, right? So let's see, f of x. We've got to do another one. P of x was x to the 5th, and I'm trying to remember x to the 5th minus, there was an x to the 3rd, there was an x squared. I'm trying to remember what it was. I have to take a quick peek back here. X to the 5th minus 6x to the 4th plus 9x cubed. Okay, so x to the 5th, come on, minus 6x to the 4th plus 9x cubed. There we go. No, that's not it. X to the 5th. Oh, I know what's happening. Whoa, we've got to change this up here a little bit so we can get, so we've got all these very small increments here. So got to get this back to sort of reality here so we can see what's going on. There we go. Okay. So here you see at this 0, we're crossing over, but we're flattening out a little bit on either side. We come up a little bit. Again, it wasn't really critical to know exactly how high we were getting to get the graph in. Okay. And then you come back down. Here's kind of a nice graph. You come back down, And at 3, you bounce back up. Okay? So let's get a little picture of that and put it in our notes. And then you'll have a little nicer picture of this function. Yeah, doesn't that look like what I just drew, right? Yeah, not really, but hey, you got the general idea here. That's all we're asking for. Okay, we crossed over, we come up, and we come back down at 3 and bounce back up. So that's it for the demo. It was a long demo. I apologize, but we had a lot of information. And the final thing in the demo is just a summary of what we've talked about in terms of the multiplicity. Again, note, in order to determine the multiplicity of a 0, you have to have your function in factored form, or else you can't do a thing. Okay, good luck with the lesson activities, and I'll be back to talk to you about that in a little bit.